Do any like
Good. Okay. Good. Yes. All they come. Yeah. Okay. Wait. Hold on. We're back. People watching at home. You apparently missed the last couple minutes or whatever. We finished it. Good job. All right. Some people were saying, I am still not satisfied. And that's the problem with rigor fetishists. They are never satisfied. They just want more and more and more. In particular, everything about the logic of this proof was completely rigorous. And as was I guess the calculus or something. I don't even see any calculus here. I just see like a bunch of weird sentences involving inequalities. But the part that's definitely informal is all this stuff here, right? So it never stops. We must, and you could completely imagine why the people of that era felt this way. We haven't really achieved anything until we have also rigorized numbers, right? Whatever the properties of numbers are, that sounds pretty important, so we need to know what those are too. Because we have reduced all of calculus to just facts about numbers. Well, what are these facts about numbers? All right, we're back. Good. So, yeah, so we did that. That was fun. The thing that makes the Epsilon-Delta definitions so great is that we can now talk about infinitely small things without actually talking about infinitely small things. The entire problem that made calculus not rigorous is that there were these infinitesimals. And what we did was, we got rid of the infinitesimals, man. And we got rid of them by we avoided talking about them. I read this thing, can you look through that thing? Is anything I write over here going to be invisible because of the properties of cameras?
What do you mean by invisible? Just write stuff.
Okay, good. All right. So if you think about what people felt about infinity in the original generation of calculus, Leibniz essentially he believed in infinitesimals. What is an infinitesimal? Can I get a definition? Yeah.
A number greater than 0 but smaller than all real numbers.
And that's really, really good. It's an infinitesimal is a number which is bigger than 0 and yet smaller than every possible real number. In other words, Leibniz believes that there exists a number, call it delta, such that this number delta is smaller than every other number. So for all epsilon greater than 0, there
Epsilon element of reals implies.
Yeah, blah blah. Yeah, sure. Okay, yeah. For all epsilon greater than 0, for all epsilon, if epsilon is greater than 0 and epsilon is a real number, then Leibniz believes that delta is between 0 and epsilon. You guys kind of see? That's the people, the generations of mathematicians who believed in infinitesimals, believed in the existence of these objects. What Cauchy and Weierstrass do is they move a quantifier, basically. And they change the whole history of calculus. They say, okay, no. Believing in the existence of these infinitely small objects is going to lead us into all kinds of contradictions, and it's nonsense. What we can't have things that are infinitely small. What we can have are things that are as small as we please. And so now, Cauchy and especially Weierstrass say, okay, no, you have it backwards, you infinitesimal people. It's for any epsilon, if epsilon is positive and epsilon is a real number, then there exists a delta, which is between. It's the exact same statement, but we just changed the quantifier scope between this and this, right? That's what the arithmetization of analysis is on a deep level. It's moving away from ever having to talk about infinitely small things. Nothing is infinitely small anymore. Things are now as small as you want them to be. Nothing is ever infinitely big anymore. Things are as big as you want them to be. And so we've tamed infinity. Do you feel it? Okay. Calculus is now about arithmetic. And we can now redefine derivatives as limits. And, okay, this is all just kind of repeat. We can redefine integrals as limits. All right, George went a little overboard on this. But just like recall from analysis 1, how we defined integral in the first place. We said, take an interval, partition that interval up into subintervals, let the norm of the partition, I may or may not have used this language, be the length of the widest subinterval. And then he liked to use the word tag, George did. Tag each subinterval by choosing a sample point in that subinterval. And then create the Riemann sum, which is the sum of a bunch of products of widths of intervals and function values at tagged points in those intervals. And we can define an integral as a limit. And these are 4 different ways of tagging subintervals by using the right-hand endpoint, the left-hand endpoint, always the largest or always the smallest. And this is a graph that shows as the number of subintervals goes to infinity.
Please pardon this interruption. The Seal of Biliteracy exam that was supposed to be given yesterday has been rescheduled for Tuesday of next week. Passes will be delivered to those students taking the exam on Tuesday. Also, this is an announcement about our fall play, Troy Story 3. There are still tickets left for this afternoon's show, 4 o'clock, which is the red cast. And there are also tickets available for the 2 o'clock Saturday show, which is the white cast. All tickets for this evening's show at 7 p.m. and Saturday's show at 7 p.m. are sold out. Thank you. Have a great weekend.
You should come see it.
No. So, I mean, I would, but I can't. Good. So, we define integrals as, for any given epsilon, okay, loosely speaking, it's like for any epsilon, but what is epsilon now? In the definition of an integral. Epsilon is like how close you're demanding the Riemann sum be to the true value,
how
right?
close the partial sum.
Yes, the integral exists only if the Riemann sum with n subintervals has a limit. Okay, I don't think we need to necessarily do all this.
This always felt kind of wishy-washy to me though, because like we have all of these different sums, right, depending on which points we like tag and consider the values of, but we never proved that all of those converge to the same place we did.
Wait,
yeah,
no,
we didn't. Yeah, we didn't at all. But in an analysis course, you do that. Yeah, Weierstrass does it. Yeah, George wants to mention that it's actually there's actually even something more complicated going on here because we're quantifying over all possible partitions or something like that.
That's hard.
Yeah. Okay, but I don't think I want to get into this. So, so it's not quite true that a Riemann integral is a limit, but it kind of is. It's the limit as.
We didn't do the partition has to be one for different partitions. But if you always have equal parts, like if you always partition it into equal sections, then you can prove it not.
But you needed to hold them all for different subgroups.
All right.